My name is Alan Kay. I work at Intel at the Open Source Technology Center. Today I'm going to talk about directly assigning Intel graphics to the guests on KVM. This is work we started recently. We're first going to start with some background information on how device operations work in the native environment, in QEMU emulation environment, and also the generic device assignment. And then we're going to cover some of the special changes we need for assigning graphics device, the Intel graphics device, to the guest. And then we'll follow by some status. In the QEMU, in the native environment, basically the device driver will find the matching device's vendor and device ID by reading the PCI config space. They can read the PCI config space by using CFA and CFC I/O ports. What they do is they write the bus function, PCI's bus function, bus device function offsets into the CFA I/O port, and then read it from the CFC. And that's how they obtain information such as the vendor ID, device ID, and such. So once they find a match, and the device driver will get initialized. And in this environment, the device hardware will automatically respond to all the I/O ports, right? So for the device usually have this MMIO memory where all the device's registers reside in, and that's how the device driver basically accesses these registers to control the device operation. And this MMIO memory is mapped, to the CPU page tables. And once it's mapped, it's mapped on cache so that whatever writes to this page will go directly to the device. So once it's mapped, the driver can access this page directly. The driver, for DMA operations, the driver will program the physical address to the device. And this is because unlike the CPU side where traditionally there's an MNU to translate virtual address to physical address, from the I/O side there's no such translation. So for the device to access the memory, it has to go through, you write the physical address there and so they can access the memory. And then for interrupts, when the DMA completes, the device will issue an interrupt to the system. In the QEMU software emulation environment, a lot of this, so many of the platform itself is emulated with software. It basically presents a virtual platform to the guest. And then the virtual PCI buses and other device models we heard earlier, they are basically hanging off on this virtual PCI bus. And then the models itself will emulate all the PCI config, MMIO, I/O port, DMA, and interrupt operations. They are trapped by the host or hypervisor, and then the requests are forwarded to the device models to be emulated. And then the QEMU also emulates all the PCI config space. Whenever early on or in the native platform where you access the CFA, CFC, the hardware will automatically respond. In this case, the QEMU will register read and write, PCI config read and writes functions to respond to the access to the PCI config space. And the contents of the PCI config space, such as the vendor ID, device ID, they are hard-coded into the device models. For example, for the Realtek NIC, it basically has the vendor ID and device ID that matches the actual hardware device, so that when the native driver runs, do a discovery phase in the guest, it will match the vendor ID, device ID of that virtual device. But then in the guest point of view, it thinks it's still talking to the real hardware. So the native driver actually gets initialized and starts to run. And the device model will just emulate the actual device behavior at the register level. So for the direct assignment case, you have early on in the QEMU emulation model where I mentioned the PCI config space are hard-coded, right? But in the device's direct assignment case, where the information for vendor ID, device ID, they actually read off from the real hardware and it's populated to the data structure. So in this case, the native driver, the actual driver, let's say you're passed to E1000 device. So E1000 device driver in the guest will actually will match the vendor ID, device ID of that path-through device, the direct assigned device, and then it gets initialized. And in this environment, some of the PCI config space, some of the PCI config space are emulated, such as bar registers. So you don't want the guest to change the bar registers on the host. So it's entirely emulated in the QEMU. The original value was obtained from the real hardware, but then once it's obtained from the real hardware, it gets emulated after that. So for example, usually what you do when you're sizing to see how large the bar is, you write all F's to that bar, and then you read off the size of the bar. And this is all done by the emulation. But other registers, such as the command register, they get passed directly to the device. So the device will still be operational, such as setting a device bus master bits. So for MMIO of the device, you basically set the GPA, guest physical address to host physical address translation, so that so once that mapping is done, the guest can access the MMIO directly without causing any VM exits. In this case, in the KVM case, you basically create a memory slot for the MMIO bar, and then when the guest accesses it, it will cause a page fault, and then the page fault gets resolved and it gets mapped. For IO port accesses, it's basically what we do in the VMCS, which basically that's the per guest data structure in the hardware, where you can actually turn on. There's a permission bit for each I/O ports. So if this particular device has certain I/O ports, you basically turn on I/O port direct access. And then once you turn that on, then when the guest accesses the I/O port, it will have a direct access without causing any VM exits. So for interrupts, the interrupts are still, when you assign a device to the guest, the interrupt from that device still gets intercepted by the host, right? So the Linux, in KVM case, the Linux interrupt handler will still seize it. And then what KVM does is they'll register a hook, an interrupt hook to the Linux interrupt handler. So the interrupts will get forwarded to the KVM direct, the KVM handler for that device. And then this interrupt from the host are then forwarded to the IO APIC device model in KVM, right? So in the KVM, there's an IO APIC model and there's a local APIC model. So the flow will go similar to how it happens in the hardware. So you basically set the interrupt in the IO APIC model, and then it will get propagated to the local APIC model. And then during the VM enter, when you enter go back to the guest, it will check the local APIC model to see if there's an interrupt pending. If there's an interrupt pending, then you set the VMCS bit for external interrupt so that when it enters to the guest, it will issue the interrupt for the guest. And then for let's say the guest finishes the handling of the interrupt, and you'll issue a EOI, and when they access the local APIC, those accesses are cause a VM exit into the KVM, and then KVM will have these device models that will emulate the access to these APIC registers. And then usually the local APIC will service that, and then whatever the subsequent effect will be propagated to the local IO, for the virtual IO APIC device model. So in KVM's case, to avoid complexity, we actually, it does not allow to assign a device that has shared interrupt, shared level trigger interrupt to the guest. So the reason is there are many corner cases when you do that. An example is, let's say if you assign a device with a shared interrupt with a host device, such as a SATA, right? So if the guest receives the interrupt and fails to issue an EOI, it can potentially, cause any interrupt that's sharing that IRQ line to hang. If it's a SATA device, you'll hang the system. Basically the system will no longer be responsive. This is not a big issue these days. When we started doing IO, direct pass-through, it was a big problem because at that time there's not a lot of PCI devices with MSI capability. Today there's a lot of, especially for devices such as the SRV, which is specifically targeted for direct assignment. They all support MSI or MSIX. And for MSI, since they're edge trigger interrupt, they're not shared, so there's no sharing problem. The one exception is that for USB devices, a lot of platforms are USB controllers do not have a MSI capability, so this could be an issue for graphics assignment case, because usually what we do is we assign the USB controller to the guest for keyboard and mouse support. So. For DMA, the driver programs a physical address to DMA engine, but however, in the guest, since you are running the guest, this physical address does not point to real memory. It's actually a guest physical address. So if if the device starts a DMA on this address, it actually will fail if you don't do anything without hardware support. So new hardware has IOMMU hardware support, such as VTD, will automatically translate guest physical addresses to a host physical address. So in this case, there's no need to change the driver at all. Driver can continue program the guest physical address to the device, and then the VTD hardware will automatically translate the guest physical address to host physical address, and things will just work. And here's just a picture of how the VTD, the structure is. Basically, it's indexed by the PCI bus device function, and then the bus device function. They have a pointer. Each bus device function entry has a pointer to a page table structure. You can think of that as a CR3 like in a CPU. It's kind of equivalent. So that's the point to the root of the page table structure. And then there are caches, that similar to TLB cache. You'll cache the translations and also the BDF indexing. Now here's an example of the device assignment. So you assign a device such as a device 100. The QEMU will read the PCI config space and register config space register, and using the sysfs file system, basically it reads the config file. And then it constructs a PCI configuration space with the information, right, for the device 100. The guest configuration access to the device 100 is handled as a pass-through device. That means the bar registers are emulated, and then the command registers are passed through. And for other devices that are not passed through, such as the host bridge device, like device 0, it's still fully emulated. All the PCI config space is all fully emulated, as we discussed before. For graphics direct assignment, there are additional changes needed. So most of the changes are in QEMU. We have a file that kind of we consolidate all the changes into this particular file. This is ptgraphics.c. Hypervisor support that are needed is due to do one-to-one mapping of a legacy VGA memory, like C002, A002 C00 memory. Another memory we had to take care of is the Intel graphics op region. And this op region, what's special about it is not reported in the PCI bar register. It's reporting a vendor-specific register. So for generic KVM device assignment, we don't know about it. So we had to do a special case set. And this op region, the purpose of the op region, if you're curious, is for the driver to get information that's set up by the BIOS. Another quirkiness about this is normally when you assign a device to the guest, the driver only accesses that device's PCI config and all resources. But in the graphics case, it actually accesses a device 0 to access some information from the host bridge. We basically access another device for information. Usually what they do, they use that information to apply some errata workarounds and stuff. That's not stuff that's not available in the device 2. So what we had to do is basically we have to in the QEMU where we do the device 0 emulation, we had to do is pass through certain registers. And this is kind of done by trial and error. So another thing it did is right now in the virtual platform, they already have a PCH device, but the Windows driver, it hard codes the modern. I mean, of course, what we have in the virtual platform is an older platform, but in today's Intel platform, the PCH device is at device 1F. So the Windows driver that will actually hard code the access to device 1F for information. For usually what they do is reading the vendor ID, device ID to see what version of the PCH it is. And since we don't have it in the virtual platform, we had to create a virtual emulated one, and then get a real device's information into this new device model.
How are you stealing the legacy VGA space from the host?
Legacy VGA space from the host. I mean, right now, I'll talk about the status. We're still working on this thing. So I think in Zen's case, I think we removed that code that does the stealing. So
it's easier for Zen.
Yeah. Right. Right.
VGA arbiter in Linux is lacking.
This is not. You don't need the VGA arbiter for this. This is a device that's already the system console, which means that it's already that way. So what you really just need to do is you need to tell you need to tell the VT system that I'm driving the graphics now and back off, and then you can map it from that. This has been supported since Linux 0.94 or something, 9.5, 9.6, something along those lines.
Mm-hmm.
Okay.
Yeah, we're going to talk about it later. So because of those quirks, we're working closely with the graphics group, to resolve these issues for future hardware. Another note I want to make about the about this assignment, graphics assignment, is that the device resets such as the FLR, they actually clear some of the MMIO registers. Where today, when we do FLR, we actually save and restore the bars, right? That's done in the PCI driver. But in this case, the device-specific registers itself is also what they do is they, in the BIOS, will set up some of the MMIO registers, the registers in the device register in MMIO space. But when you do a reset, it will clear some of it. And then because of that, you lose some of the functionality.
Don't you run the device BIOS again in the guest? Don't you assign the same PCI, the device BIOS, so that it can initialize it again?
We signed a device BIOS, but I think this one probably done by system BIOS, so you don't get that benefit. So one of the things we can do is we can save and restore, some certain ranges of MMIO registers. So I've added another option for the VGA parameter is to do a pass-through, and then you just use the standard device assignment syntax to assign the graphics, integrated graphics. I also added another. Currently in the QEMU, there are two functions to read and write PCI config space, but they only kind of work for the assigned device. So since in this case we're to read the config space for the device 0, so we kind of need a function to pass the bus device function as a parameter. So we kind of temporarily we just add a couple more functions. And then for graphics related hooks, for assign init function, we added a function that does copy of the ROM content to the C00 memory. And then in the assigned device register regions, we register the VGA compatible MMIO and IO resources. For the hypervisor, because we have to do some one-to-one mapping, I think when I looked at the KVM, there's a one IOPTO that maps a one single page that does one-to-one. I think that's for supporting real mode. So for temporary, I add another IOPTO that allows it to map multiple pages. Status, right now we finished the coding part of the enhancements for the stuff we think we need, and then we're in process of bringing up the NDBug. I mean, currently I initially started with a Windows guest, and then I tried Linux guest. Seems to be a little more easier because there's access to the source code. So currently there's some issue with finding the VBT table, the video BIOS table. Also, we're working with the graphics team to resolve a lot of these virtualization issues. Hopefully, they'll improve in the future. And that's all my talk. Any questions?